Alright, hello everyone, and welcome to our lesson on Earth's resources. Now, to begin, I want to talk about this word, resource. We're going to use this throughout the lesson. It's important to understand what we mean when we say resource. A resource is something that we can use, something that people can use. So a few examples of resources would be metal, wood, ceramic, cotton. Remember, we use all of these things. We use metal to make cars and bridges and skyscrapers. We use wood to make homes and furniture. We use ceramic to make things like plates and cups. So a resource is just something that we can use. Let's move on to slide 2. Today we're going to be looking at two main types of resources. We're going to look at two categories. That first category, renewable resources. To renew means to replace. Here, in our definition, renewable resources can be replenished over a fairly short span of time, such as months, years, or decades. Examples of renewable resources would be, well, wood, which we mentioned earlier. We know that trees provide wood. We get wood from trees. We have farms where we plant trees. So trees can be renewed. They can be replaced. Other examples would be many of our food resources. We know that, for example, chickens, pigs, cows. We know that chickens provide eggs, cows provide milk, pigs provide meat. If we raise these animals in a responsible manner, they are renewable because we can sustain that type of farming. And that's what farmers try to do. They try to raise these animals in a responsible way so they can be replaced. So wood and food would be examples of renewable resources. We're also going to look today at that second category, non-renewable resources. These are resources that take millions of years to form and accumulate. Examples of non-renewable resources are oil and natural gas. We can't just go out and make new oil. We can't just make new petroleum, new coal, new natural gas. Remember, if you've seen our lesson on minerals and on rocks, you understand that a lot of these resources, like coal, are created by organic material that becomes buried under layers of sedimentary rock and then is forced down into the Earth's surface, where that rock becomes metamorphic. And that it's that trapped organic material that becomes the fossil fuels like oil, coal, and natural gas. But that takes millions of years to happen. We can't just go out and make new oil. Continuing that point, on slide 3, fossil fuels are hydrocarbons that may be used as fuel, including coal, oil, and natural gas. A hydrocarbon is a molecule that is made of only hydrogen and carbon, and hydrocarbons are combustible, which means they can be combined with oxygen to create products such as water and carbon dioxide and carbon monoxide. And when they do this, they release chemical energy in the form of heat, and we can use that heat energy, we can convert that into other types of energy. All right. On slide 4, you see a good example of how we can get this oil and natural gas, where it comes from. Remember from our lesson on rock, we learned about the formation of sedimentary rock, where we have different layers of sediments, of sand and mud and organic material that form different layers. And as those layers are compacted, they're put under enormous pressure because of the weight of all the material on top of them. They form rock, and as they are forced down, and so they form sedimentary rock. And remember, after they form sedimentary rock, they are often pushed and pulled and distorted and heated by different forces, and that forms the metamorphic rock. And it also forms those curved layers that we see here. You can imagine the layer in this picture like a layer of sedimentary rock that's being pushed from the sides and has been pushed up to form kind of a bulge. And underneath that layer of rock, oil and gas have become trapped. Something else to notice about this picture, underneath that layer of brown rock, we have a layer of gas, a layer of oil, and a layer of water. I think by this point many of you have seen the science experiments where we take oil and water and we pour them together. We see that oil and water do not mix, and we know that the oil will float on top of the water because the water is heavier than the oil. The oil is lighter than the water, so it floats on top. The same basic thing is happening here underneath the surface of the earth. We have a lot of water and a lot of oil and a lot of gas. That oil and gas will float on top of the water. And that's how we can drill down into the earth and extract it. This is just one way for us to get oil, by going into drilling underneath this cap rock, which we call an anticline. Another way is described on slide 5. We have tar sands and oil shale. Fuels can be derived from tar sand. They could be good substitutes for dwindling petroleum supplies. One of the problems with tar sands is it can be very dirty to extract. And just getting the oil out of the sand can cause a lot of pollution. The next slide, number 6. Some of the most important mineral deposits form through igneous processes and from hydrothermal solutions. Remember what we learned about igneous rock? This is rock that is magma in the earth, that liquid rock. When rock actually is crushed and melts into magma, when that magma cools, it freezes and forms crystals, and that's our igneous rock. We also learned about hydrothermal solutions in our last lesson. Remember, these are solutions of water and solutes. For example, a salt. We all know that salt is sodium chloride. We know that that compound will dissolve in water, and more of this salt will dissolve if the water is hotter. So when the water is very hot, more solute will dissolve. When that water, so that hot water underneath the earth that's heated because of all that heat and pressure deep in the earth, that hot water can actually carry a lot of elements and minerals as solutes. And that hot water can deposit all those solutes in igneous rock to form new compounds and new types of rock. Ore is a useful metallic mineral that can be mined at a profit. You can see a good example of this on slide 6. We see that mineral-rich hot water seeping into rock fractures. Alright, so there at the bottom, at the bottom of the picture, you can see those layers of igneous rock. And at the very top of those layers, we can see a lot of red. Well, that's that hot liquid magma, the rock that is so hot that it's actually melted. It's become a liquid. And remember, when that rock is in liquid form, the molecules are farther apart and moving freely, so that hot liquid magma is going to be lighter than the igneous rock, and it's going to try to rise, and it's going to shoot up through those fault lines along with the hydrothermal solutions. So you get that liquid magma, the liquid rock, and the water with all of those solutes like sodium and chlorine, like sodium, magnesium, chlorine, calcium. The water, so both of those go up through those faults together, and that creates the veins that you see on the right side of the picture, those red veins of liquid rock mixed with the hydrothermal solutions to create these ores. And those ores often contain very valuable minerals and very valuable elements like copper and iron. Next, slide 8. Non-metallic mineral resources are extracted and processed either for the non-metallic elements or for their physical and chemical properties. A good example of this, well, we've seen several examples on the next slide. There's a huge table there of non-metallic minerals. On the left side of that table, we see a lot of different minerals. They're listed in alphabetical order from apatite all the way down to talc at the very bottom, and we can see a lot of different uses of those minerals. For example, apatite contains phosphorus, which is very useful as a fertilizer. So that apatite can be used to make phosphorus fertilizer. Um, Going down the list, look, number 4 on the list, clay minerals. Clay minerals can be used to make ceramics. Going down, number 6 on the list, one we're probably all familiar with, diamonds. A diamond is just crystallized carbon. Diamonds can be used as gemstones, they can be used for jewelry, or they can be used in industry as abrasives. Because they can be used this way because a diamond is the hardest substance on Earth. So a diamond can cut just about anything. So they're very useful for making strong blades or very strong drills. So just go down the list, take a look at these different non-metallic minerals: fluorite, garnite, gypsum, halite. Notice we have a lot of gemstones there like diamonds and garnets. We also have elements that can be used in glass like fluorite, and a number of different fertilizers as well. Okay. Let's move on. We're now going to move into talking about our renewable resources with alternative energy sources. One of the most popular alternative energies today is solar energy. This is when we can actually convert the light energy of the sun into electrical energy using a photovoltaic cell. As we see on the slide, solar energy has 2 advantages. The fuel is free because the fuel is sunlight. So until we run out of sunlight, we'll always have the fuel for solar energy. Number 2, the second advantage, it is non-polluting. There's no pollution from solar energy. It's not like we're burning a fuel. We talked earlier about hydrocarbons, and how we burn these hydrocarbons for fuel. Well, when we burn them, we produce carbon dioxide, we produce carbon monoxide, and we often produce a lot of other compounds that we don't want, like sulfur dioxide and as well as lead compounds. With solar energy, you don't get any of this. It is non-polluting. The next alternative energy, nuclear energy. To do a very quick review, we spoke in a previous lesson about the subatomic particles in the atom. When we did our lesson on the periodic table, we talked about subatomic particles. We know that the protons and the neutrons are there in the nucleus, and the electrons are the much smaller particles that move around the nucleus in different energy levels. We also learned, if you will recall, that the protons in the nucleus have a positive charge, and we learned that the electrons moving around the nucleus have a negative charge. Oh, hello. Oh, there we go. Well, we learned that those opposite forces, the positive charge and negative charge, attract one another. Let me see. We also learned that similar charges, for example, 2 positive charges, will repel one another. And remember, we talked about magnets. We all know that the two north ends of a magnet will repel. But if we have the north end and the south end, they will attract. The same is true of charges. Well, we have to ask the question now, if these two charges, if two positive charges repel each other, why can they be in the nucleus together? And I'll give you the example here of a helium atom. A very crude drawing, but we know that a helium, helium's atomic number is 2, meaning that it has 2 protons and 2 electrons. There we go. 2 protons and 2 electrons. So if these 2 protons repel one another, then why are they being held together in the nucleus? It doesn't seem to make sense. And the answer is that there is a much stronger force holding those protons together. It's much, much stronger than that repelling force. We actually call it the strong nuclear force. Because that force is so strong, when we break it, we release a lot of energy. You can think of maybe 2 teams playing tug of war. And if you're pulling very, very hard on that rope, but you're not moving the teams aren't moving, but they're still exerting a lot of force pulling on that rope. Now, if I was to come up and cut that rope at once, both of the teams would fall down. There would be a huge release of that potential energy. The same kind of thing happens to the nucleus of a uranium-235 atom. When we bombard it with neutrons, that nucleus will actually break. And so when that strong nuclear force is broken, it's just like the 2 teams that fall down when I cut the rope. So when we break that nuclear force, we release a huge amount of heat energy. And that heat energy is usually released in the form of gamma rays. And we can actually harness that in a nuclear power plant. And there is an example of a nuclear power plant on page 12. One of the advantages, one of the good things about nuclear energy is it's very efficient. A nuclear power plant like this one can put out a lot of energy, much more than wind or solar. The main drawbacks, the bad things about nuclear energy, we do end up creating radioactive waste. When we create nuclear energy, the carbon rods that are left over are radioactive, and they have to be disposed of in a very safe way underground, and it's very difficult and very expensive to do this. There are also dangers about the release of radioactive fuel if a reactor core is damaged. We all remember we saw this last year when the tsunami hit Japan. There was a nuclear power plant right on that coast, and for a long time we were very worried about the damage to the reactor core and nuclear fuel leaking out. And here we are a year later, they are still dealing with that problem. So that's a possible negative side to nuclear power. Next, continuing with alternative energy. The first alternative energy, wind. As we see on slide 13, in the next 50 to 60 years, wind power could meet between 5 and 10% of the country's demand for electricity. Wind, like solar, it's very clean. You don't have to burn any hydrocarbons like you do with coal or oil. You don't have any radioactive waste like you do with nuclear. The problem with wind is, what happens when there's no wind? I'm looking out the window right now, and the wind isn't blowing. So if the wind's not blowing, you can't generate electricity. So it's a little unreliable. Clean but unreliable. On slide 14, you can see a picture of some wind turbines. You can understand there the wind is pushing those turbines, and the turbines are turning generators to generate electrical power. However, yeah, very clean, not making any pollution, but what would happen if there was no wind? The turbines would not be turning. The next one, hydroelectric power. That's the power generated by falling water. Water is held in a reservoir behind a dam, and it's a form of stored energy. Now we can release that water to produce electric power. You can see an example of that on slide 16. We have a picture of Glen Canyon Dam. You can see that dam down in the bottom right corner of the picture. It's holding all of that water back. Well, what would happen if we opened a gate or we opened a door in that dam? The water would rush through very quickly. If we put a turbine there, that water will rush through, it will push the turbine, it will rotate that turbine and turn a generator to generate electricity. So that's how we can generate electricity from hydroelectric power. Hydroelectric power, some good things. Like wind and solar, it's very clean. We don't make any pollution. It's also very reliable. Look at that dam. We don't have to wait for a sunny day like we do with solar. We don't have to wait for a windy day like we do with wind power. We could produce hydroelectric power in any type of weather. However, there are problems with hydroelectric power. What happens if we look at that dam, look at all the water behind the dam. Now, before they built the dam, that was just a small river. So when you build a dam, the water level will rise, and it's going to cover the land behind the dam. So what happens if that's good farmland? What happens if people live there? So to produce hydroelectric power, you do lose some land because the land is covered in water. So anytime a hydroelectric dam is built anywhere in the world, there's always a problem. If you look especially at India and Africa, when they've built every time they've built hydroelectric dams, they always have to move a lot of people, and then many times they lose their homes and they lose their farms, so they lose their jobs as well. So that's a problem with hydroelectric power. Also, another problem might be the ecosystem. What happens to the fish that live in that river? Maybe they cannot live in the lake that you produce. So you disrupt the ecosystem to create hydroelectric power. So again, like every source, there are good things and there are bad things. Another, geothermal. Remember back in our picture that we looked at on slide 15, we saw that water and oil and natural gas trapped under the anticline. Now, sometimes you could have an anticline, but no oil and no gas. It might just be water underneath that anticline. It might help to go back and look at that picture on slide 5. When you look at that picture on slide 5, try to imagine that anticline with no oil and no gas. It's just water. Well, that water is becoming very hot. It's being heated by all that hot magma underneath the earth. So as that water gets hotter, the water boils and produces steam. So geothermal energy is when we harness that energy. So that hot water is used for heating and to turn turbines that generate electrical power. Imagine, if you will, a kettle or a pot of water sitting on a stove. If we turn on that burner and we boil that water, all that steam is going to rise. We could put a little turbine there, and that steam will push the turbine. That's basically what's happening with geothermal energy. We can use the steam from that water trapped underground to push a turbine, turn a generator, and generate electricity. You can see a picture of this on slide 18. You see that white steam coming out of the earth. That's because there's hot water, so much hot water boiling underneath the earth. We could put a turbine there and use that steam to push the turbine and generate electricity. Another source is tidal power. We all are familiar with the tides. This is when the oceans rise and fall because that water is being pulled by the gravity of the moon. So tidal power is harnessed by constructing a dam across the mouth of a bay or an estuary in coastal areas. There's a picture of that on slide 20. You can see that dam that's built across the bay. The ocean's in blue there on the left. The top picture, we see that ocean and the bay at low tide. In the second picture, we see high tide. The water rises. So the water rises and we let water into the bay. Then, when the water falls, all of that water is still trapped behind the dam. It's still trapped on the right side. So the ocean falls on the left, the water falls on the left side, but it does not fall on the right side. It's trapped. Then we have basically a hydroelectric plant, just like the dam that we saw a few slides earlier on slide 16. This tidal power plant works the same way. We can release the water that's trapped on the right side of the dam. That water rushes out, and that can push a turbine and turn a generator and generate electricity. All right, so now let's expand this discussion into water, air, and land resources. First, let's talk about water. We know that water is a resource, just like all of the other resources we've talked about. Remember, a resource is just something we use. For example, we talked about using oil for energy. We talked about how we use metal to build bridges and to make cars. We use wood to make furniture and to build homes. Every day, people use water for drinking, cooking, bathing, and for growing food, for farming. We can use fresh water, like in lakes and rivers. We cannot use the salt water in the ocean. We cannot drink ocean water. We cannot use ocean water for farming. On the next slide, we are talking about freshwater pollution. Now, pollution can take a lot of different forms, and we're going to look at a lot of those on the next slide. But when we talk about pollution, we look at two main types of pollution: point pollution and non-point. Point comes from a known specific location, such as a factory or a power plant. Maybe we have a oil or natural gas power plant that is releasing lead or sulfur dioxide or dioxins or carbon monoxide into the water. That would be point pollution. Non-point is pollution that does not have a specific point of origin. This would be like the pollution from thousands of different cars, or pollution that comes from acid rain. Maybe the air will become polluted from a factory. Then that air pollution spreads out over a large area and pollutes the water. The thing to remember here is that point pollution, like from one factory, just with one, maybe a factory with one pipe going into a river, it's very easy for us to see, it's very easy for us to understand, and it's very easy for us to stop it. It's that non-point pollution where we have pollution that's spread out over a large area. It's often very difficult for us to see. It's difficult to understand, and it's difficult for us to stop it. On slide 23, page 23, we see a lot of different types of water pollution. Examples would be bacteria and viruses. That would come from wastes. We could see wastes that remove oxygen from the water. These would be, again, like bacteria. The example there, we see animal manure and plant debris that bacteria decompose. In particular, an example of this would be nitrates, such as from nitrate fertilizer or from animal waste from farms. For a lot of bacteria, those nitrates are a source of food, but when those nitrates go to work, they remove oxygen from the water. And so that water has no oxygen, so the fish are unable to breathe. So we end up killing the fish. Other types of water pollution, organic chemicals, those are our hydrocarbons that we talked about earlier, like oil. We also have problems like pesticides, pesticides which farmers use to kill insects, the herbicides that farmers use to kill weeds. All of these are poisons that can end up in the water, and they're another source of pollution. I do want to look at the second one from the bottom, sediments, soil that can be a source of water pollution. That comes from erosion, and we are going to talk about that towards the end of the presentation. How that soil and that erosion can become a source of water pollution and can create major problems. But let's move on for right now from water pollution to air. The chemical composition of the atmosphere, that blanket of air around the earth, almost like the skin of an apple. That air is the atmosphere that helps maintain life on earth. However, there are many different things that people do that can pollute this air. A good example there, the increase of carbon dioxide in the atmosphere has altered the carbon cycle and contributed to global warming. Remember, we learned about the combustion of hydrocarbons like oil and natural gas and coal. Remember, in combustion, those hydrocarbons combine with oxygen to create water and carbon dioxide. So water and carbon dioxide are the two main products of the combustion of hydrocarbons. Well, we've already talked a little bit about the greenhouse effect. We understand the problem that carbon dioxide poses. Very briefly, you remember that the Earth, that solar radiation comes to the Earth from the sun in many different forms. And some of these forms are very high energy, have a lot of energy, and some have less energy. One form of solar radiation is visible light, the light that we can see. Now, a lot of this light strikes the Earth's surface and it is reflected by the Earth. So that light, so the Earth reflects that light. So the light kind of bounces off of the Earth. The visible light hits the Earth and bounces off. Now, in the lesson on the greenhouse effect, I gave you the example of a football. Now imagine if I take a football and I drop it from, let's say I drop a football from this high. It hits the ground and bounces back. But it does not bounce as high as my hand. If I drop the ball, maybe it only bounces to here, because that ball loses some energy. It has less energy. Well, the same thing is true of the light that hits the Earth. Visible light hits the Earth, but when it bounces back, it has less energy. So it bounces in the form of infrared light. Infrared light which has less energy than the visible light. Now, usually, that infrared light, that light with less energy that bounces off of the Earth, normally that infrared light just goes out into outer space. But carbon dioxide actually absorbs infrared light. So if there's more carbon dioxide in the atmosphere, more infrared light is absorbed. So more heat energy, the heat energy of that electromagnetic radiation stays in the atmosphere and is not reflected into outer space. And this is what we call the greenhouse effect. So the increased carbon dioxide creating a warmer planet. Another problem is when air pollution can cause acid rain, when pollution can be converted into an acid which can then fall along with rain. Here we see some of the major, on slide 25, some of the major primary pollutants. You can see the biggest one on the bottom of the chart, carbon monoxide. Causes all kinds of problems. We also see the nitrogen oxide. These are the nitrites and the nitrates that can cause a bloom in bacteria and algae and remove oxygen from the water. We also can see volatile organics, sulfur oxides, in particular sulfur dioxide, which can come from fossil fuels, and small particulates. On the bottom, you can see where they come from, and you can see that the biggest source of carbon monoxide and sulfur oxides is transportation. That's cars, planes, buses. So transportation is the biggest source of these primary pollutants. You can also see other sources, industrial process and fuel combustion. That's like power plants. Let's look there at land resources. Earth's land provides soil and forests as well as mineral and energy resources. I mentioned earlier we were going to talk more about erosion and how sediment gets into the water. We're going to look at that right now. Because remember, that soil, that land is a resource, just like the water and the air. We have to think of land as a resource, something that we can use. And just like water and air, it can be polluted and it can be damaged and destroyed. We see there in the second point, mines produce mineral resources, but many mines can destroy soil and vegetation. Mines can also cause erosion and water pollution that contaminates soil and water and destroys ecosystems. You can see an example of that on slide 26. We see a beautiful forest, and there in the center of the picture, that big brown mine. That's an example of surface mining. Think about what they've done here. There's a large area where, to make that mine, we have to go in and we cut down the trees. Well, now, if there's no trees, there are no roots in the soil. So there's nothing to hold that soil. So that soil is washed away by rain and by streams. Remember when we talked about sedimentary rocks, we learned about how water, how streams and rivers can carry all those particles, can carry the sediments. Well, when we cut down all of the trees, that happens much, much faster because there's nothing to stop it. There are no plants to hold that soil in place. A lot of those plants, their roots are like fingers. They're like hands holding that soil. You take them away, the soil just washes away. All of that soil ends up in rivers and streams and can cause problems for all of the plant and animal life there. So finally, let's wrap it up. Keeping water clean and safe. Conservation means using things carefully. Remember, we have to use water. We can't live without it. We have to use air. We have to use forest resources. Conservation does not mean we stop using them. It just means we're careful about how we use them. Pollution prevention means stopping pollution. Let's look at some examples of conservation and stopping pollution. We see there, starting in the 1970s, the federal government, that's in the United States, we passed several laws to protect our resources, such as the Clean Water Act and the Safe Drinking Water Act. This was about eliminating point source pollution of surface water. The next page tells us things that we can do as individuals to prevent water pollution. Don't pour household chemicals down the drain. Things like paint, paint thinner, detergent, pesticide. When we pour these down the drain, they end up in our streams and rivers. Never dump toxic chemicals in the gutter or on the ground. Toxic chemicals, especially in batteries. One example you might not think about, in batteries, the acid in those batteries can be toxic and is a bad source of pollution. They have to be disposed of properly. Just like we learned about with nuclear waste, we have to build a special place to dispose of the waste. We have to do the same thing with a lot of these toxic chemicals and battery acids. And that's a little bit more in point 3. Don't put these in the trash. Old computer monitors and batteries, don't put them in the trash. They have to be disposed of properly. The next point, find out about the hazardous waste collection sites in your neighborhood and in your town. Find out the right place to bring those batteries, the correct place to bring those computer monitors, or all that old cooking grease. And avoid using hazardous substances in the first place. Don't use pesticides if you don't have to. Don't use chemical herbicides if you don't have to. In the 1970s, Congress passed the Clean Air Act, which was the most important air pollution law. This established our 6 different pollutants that cause health problems, such as carbon monoxide, ozone, the lead compounds, the sulfur dioxide, the nitrogen oxide, and the particle matter. Right? The next page tells us things that we can do to save energy so that we use less fossil fuels. Recycle, let the sun in on bright winter days. That way we use solar energy to warm rooms. Use energy efficient light bulbs. Turn off electrical appliances if we're not using them. Walk or ride a bike when we can. Remember, we saw earlier that the #1 source of air pollution is transportation. So if we walk or ride a bike instead of driving a car, we're doing a lot to help the environment. When buying electric products, look for the Energy Star sticker. That shows us products that are saving energy. More ways to care for the land resources: compost and recycling. That helps us to compost and recycling. They're going to help us to throw away less. We produce less garbage, so we don't have to use huge amounts of land to dispose of all that garbage. We don't have to make huge landfills. Right? So that does it. Our unit on our resources, some of the threats and the problems that are posed to our resources, and things that we can do to protect our resources. All right. Thank you all very much for tuning in, and I will see you next time. Well.